All right, so my name is Jonathan Christian, and here we are going to do a problem in heat transfer, and we're going to try to make this as real as possible, and also as practical as possible so you can get a good understanding of how heat transfer works. So today we are working in Alaska, and we are working for an oil refinery. We are an engineer, and our job is to take care of the growery division. So we're in a remote location. We have a beautiful indoor growery, and right now we want to expand this. The only thing is to expand it, we need more light, we need more energy, and we're going to have to double our power, and we want to increase our power output. We want around double. It's a little more than we need, but it'd be better to have double and not need it than to make a little too little and need more. So right now, to run the entire operation, we are using a KTA 50 G8 Cummins generator and motor assembly. So we have our motor right here, our generator that generates our power, and our heat exchanger right here. We're modifying our motor. We're changing out the fueling system. We're going to try to run on some different fuel, changing out some components, extending the drive line on out, and we're going to double the generator and just put a whole other one on there and see if we can't make this work. However, doubling this generator means that we are going to be changing the amount of energy that needs to be dissipated out of it. So right now we're going to assume it's probably going to be double. Our goal is to work over here with the heat exchanger. We need to design a heat exchanger that will dissipate the new amount of power. So we look at our data specification sheet. We go online, we find out what we can about the motor. Maybe we had it back somewhere and we had it on site to look it up. So the first two pages are going to give us what we need. The first two pages about the engine and the cool pack data, which is just the heat exchanger data. The rest of it's mostly going to be about the generator. We toss it out. We don't need it. When we take a closer look, we get cool pack performance data. This is our heat exchanger. Tells us how many pumps. This is really important. It tells us the fluid that is being used with the coolant. So we're trying to do as minimal changeover as possible. We don't really want to change the fluid if we don't have to. So right now we're at 50% ethylene and 50% water. Ethylene is just an alcohol. It's just an antifreeze. Alcohol freezes at lower temperature, so if the motor gets cold, the water shouldn't freeze. We look on down to limiting ambient temperature. So this is going to tell us our maximum hot temperature going in. This means how hot the air can be and safely run the machine before overheating starts to happen. We also get our cooling system airflow. This is just another way of saying the volumetric flow rate of the air going into that heat exchanger. That's all it's saying. And we get it for free. We are also going to check the weighted dimensions. So the important thing for us, we don't want to change the overall profile of the motor the way we have it, but we are open to change the length of the motor. So it's important to keep that width and length that height and width about the same. And we also get the fuel consumption. This is a way to measure how much energy is being dissipated into the heat exchanger. There are two ways to measure the energy going into the heat exchanger. One, we do a control boundary around the heat exchanger, and that will tell us how much energy is going in if we measure how much is coming in through the pipes. Or two, we do a control boundary around the motor, which means we have to account for the cold air going in, the hot air going out, the energy going to the generator in form of mechanical, the dissipation of heat through the actual motor, which means radiation and convection. We don't really want to touch it. There's nothing nice and neat about this motor when it comes to cooling. The loss of the pipes, and then finally, when we subtract all that out, we know that the rest of that energy should be going to the heat exchanger. That's one way of doing it. Or we stick some thermometers on the incoming and the outcoming, and we get a good idea. So we are going to just stick some temperature gauges, find out what the maximum safe operating temperature is, and save us some time. So next step is to clarify what we found. We know the volumetric flow rate from the data sheet for the motor. We know what type of heat exchanger we want. It's a tube and shell. We know that we're using air on the outside. We know that the maximum safe limit for the cooling fluid is 400 Kelvin. So we're going to assume everything's at the maximum temperature. It's the worst day ever. It's important when you do that because when everything's at the worst scenario is when we want to run our equations. We don't want to run them when it's nice outside and there's rainbows falling from the sky and puppy dogs. We want to run them when everything is really bad. So that way, when everything is bad, we're still okay. So the heat going out, we measured this. We tried to get the motor a little bit hotter than usual and measured the heat coming out under adverse conditions. The air coming in, we got that from our data sheet. Our data sheet told them the maximum safe limit at 48 Celsius. And then we get the heat temperature going out, which is a rough estimate of 108 Celsius. So we got that again from measurements under kind of rough conditions that we put the motor under to check. And remember, we convert all these to Kelvin. Don't make the mistake of leaving them in Celsius. It is a mistake. You will have problems in heat transfer if you leave your temperatures in Celsius. I know it's easy. I know it makes a lot of sense, but it's really easy to make a mistake when you're putting stuff in Celsius instead of Kelvin. Now we go to our mass flow rate. Our mass flow rate is 5 kilograms per second. It really began at 2.5 kilograms per second in our current model, but we're assuming double the power output, so we're just going to say it's 5 kilograms per second. And we know the fluid, it's 50% water, 50% ethylene on the cooling fluid. We know our height, we need to go find that. Now, the width is 2 meters. That was gotten back here at our dimensions page. It's 2 meters. Height is 2.5 meters. Doesn't have to be perfect. It's an approximation to design from. So our height is at 2.5 meters. Well, the maximum height is right here. This is not part of your heat exchanger, the actual exchanging of the heat at least. It's part of the control system, it looks like, but not part of what is actually exchanging heat. And nor is the base. The whole base of this unit is not exchanging heat. So only this area right here is exchanging heat. So we're going to say this is 2 meters. It makes a lot of sense because that fan is a circle and it fits neatly into a square. And we already know the width is 2 meters, so the height is going to be 2 meters on the actual area exchanging heat. Now, that was the basic information. We did some digging, some on-site measurements, and then we got what we needed to actually begin the problem. Now, I would like to give a moment for all the credits for the images that we got and used today. Now, moving on to our heat exchanger. Sorry about that. There. So moving on to our heat exchanger. What's the first thing we do when we start a problem? We have a beautiful blank page and we need to solve this problem. We write down our known values. That's the first thing we do. What's the height? 2 meters. What's the width? 2 meters. What's the volumetric flow rate? Well, that is 28.8 meters cubed per second. Always take the time to write air next to it so you don't forget it. You don't want to make that mistake on a test. What is the fluid information for the water? It's 5 kilograms per second. So 5 kilograms per second, and that's for the water. All right, and we have our T input is 400 Kelvin. Our TH output is 350 Kelvin. Now this is for the water. Remember that your hot here is the water because that's the hot stuff. So make sure to make a mental note what's hot and what's cold. Now our cold coming in is the air. That's going to be our cold. And that was 321 Kelvin. And then our cold going out, which we also measured, is 381 Kelvin. Okay. We also want to know what this looks like. So what's going on here in this heat exchanger? Well, we got some really hot air coming. We got some really hot water and alcohol mixture coming in. And that right there is ethylene. Sorry, I forgot to write ethylene there. It's water/ethylene. So we have some really hot coolant mixture, water and ethylene, coming in. This is THN. And what's it go out as? It goes out as a cooler temperature. Bam. So now we have our inflow, our outflow on the hot, and a rough estimate of the path it's going to take. Now we have our cold coming in. Our cold coming in is the coldest value here. Starts over here. Remember, a tube and shell heat exchanger is going to be based on cross flow as much as possible. It saves, it runs more efficiently that way. So we have our T cold coming in. We know that's colder, and we know that our T cold going out is hotter. And again, we have a logarithmic style path. So this is our heat exchanger. This is what it looks like. Remember your heat exchanger. The hot coming in is hot, the cold going out is warmer, and the cold coming in is cold, the hot going out is cooler than it started. Remember that. And also it's important to remember your maximum temperature difference in this system. It is the T hot coming in minus the T cold coming in. That is your max delta T. That's important when you're doing the analysis. So we move it on down. Now we want to find values. So there are a couple different ways to approach the problem. One of them is to start your calculations and get your values when you need them. But if we want to be neat and we want to do things in a professional and nice way, I recommend you start by getting your values. Where do we get our values from? We get them from your favorite heat transfer book, the one that you love, the one that you need in a hardcover, the one that you just tear up and you write stuff all over so you can find it. We need it from that. How do I take my values? Well, I'm glad you asked. We have our T hot coming out, our T hot coming in. We want what? To take it at the place where it's coming in hot, those values, they're only applicable at the beginning. How about going out? Only applicable at the end. In between there, those values are going to change. Your viscosity is going to change. Your CP is going to change. And it's not going to be constant. So we take it from the mean temperature, which is a linear average. So we have our T hot coming in is THM, and we have our T hot, our T median, which is a function of T hot coming in plus T out coming in over 2 is going to be 400 Kelvin plus 350 Kelvin over 2. Now our mean hot temperature is going to be 375 Kelvin. Bam. Highlight your important numbers. Where do we look now? We look to table A-6. We open up our trusty book. We go to table A-6. Now, we get our table out. Make sure to know where this is. Always make sure to check your units. Know what you're looking at stuff in. So let's take all the values that we might use, and put them down here. So when we need them, we don't have to go back to this big book. We'll just have them right there on our problem. All right. So when we're doing that, we're going to want our specific volume, and we're taking all these values at this temperature. Now remember, your water table goes in terms of 5 degrees Celsius, so 375 Kelvin is going to work perfectly. And remember, keep your temperatures in Kelvin. I've done this in Celsius before. It wasn't pretty. I looked up the value in Celsius. It did not help me. So let's look here. 375 is going to get us 1.045 e to the negative 3 meters squared per kilogram. Now here's the thing. I want density. I don't want specific volume. Specific volume's a little harder to conceptualize, and we really want to stick to that density, right? So density is just the inverse of specific volume. So when you put 1 over this number down here, up here, you're going to get roughly 957 kilograms per meter squared. We run through, we get our CP value. CP value is important. If you're looking in your book right now, CP value is in terms of kilojoules per kilogram Kelvin. The problem is kilojoules isn't a base unit. Everything you write down here is best when it's left in its base units. So we have, instead of 4.22, we have 4,220 joules per kilogram Kelvin. I always recommend that you convert these things to your base unit. If you leave any of these other units, you run the risk of making a mistake later in your equations. Now we get our viscosity. Remember, this is the absolute viscosity. There are two viscosities. One where we divide by the density, and one where we don't. So this is just the straight viscosity. No density is a part of this function. We have our K. Remember, K is your thermal conductivity, is how well your water conducts without mixing. So when we treat it as a solid. When it's not mixing, it's just transferring heat. And our Prandtl number, which is a beautiful non-dimensional number in fluids, has a lot to do with how well things mix. Essentially how well, when you push fluid across a space, it's going to mix that fluid across its boundaries. So we got all that for you now. Bam. That's done. Now what do we want to do? We want to find our air values. That's really important. So let's calculate our T cold mean. Again, it's going to be equal to these two values added together. No big deal. So we have 381 Kelvin plus 321 Kelvin over 2. That T cold mean is going to equal 351 Kelvin. Now, where do we go for this 351 Kelvin? Table A-4 in your book. That's where we're going for our Kelvin. You flip it open, and we don't have a value for 351 Kelvin. We have a value for 350. What do? Well, we just assume that 350 Kelvin is close enough to that 351 is close enough to 300. It's not going to be a problem. Unless there's a large difference in your values across the table between your temperatures, go for the temperature that's closest. If you're concerned that's going to be a problem, You might want to interpolate, but we do have a lot of things to do in our day, so don't worry about interpolating if it's going to be close. And that is somewhat up to your discretion. So we get our density as 0.995. Now remember, the density of air near atmospheric pressure should always be around 1 at atmospheric pressure, atmospheric conditions. That CP again, remember, take that CP, convert it to its base units. Don't make that mistake. I've made that mistake before. I did not like that I made that mistake before. So let's not make that mistake. We get our absolute viscosity, and we get our dynamic viscosity, which includes the density. And if you notice, when you run the numbers through, they're very close in this case because that value for density is near 1. So that's good to remember. And we get our thermal conductivity again. We have a very, very low thermal conductivity for air. It makes a great insulator when it's not flowing. And we get our Prandtl number, how well these fluids are going to mix, essentially, and some other things factored in at 0.7. Bam. We are done with this section. We now have what we need. So our next step is we need to design a heat exchanger. We need to take a heat exchanger and we need to design one. Now this is going to come into a lot of different factors. When you're designing a heat exchanger, you have a lot of different constraints going on. You have company favorites, you know, what your company really wants you to do. You have what you trained on, what you know well. And there are so many design criteria when you're doing this. But let's just take a quick sketch and take a look at what we're working with. We're essentially working with 2 meters by 2 meters in a section. So I went ahead and made some design choices for you. We have 1,000 tubes, so N equals 1,000 here. And we're going to run it as a single shell pass. So we have one shell, this pipe here, we're running down. We have one shell. We're not dividing it into 2 parts and mixing more air in. It's just going to go, that air is just going to go all the way through. All the way through. And how about the pipes? So we have our pipes, and we want to do a double pass on the pipes. So our pipes, they come in, they go back out. They come in, they go back out. That's a double pass. We have 1,000 of these. What's our diameter? We're going to get a diameter of 0.01 meters or 1 centimeter. We happen to have a lot laying around right now. That's what we're going with. When we do this, we're going to make some assumptions. So we have this pipe here. This is our pipe. It's some copper pipe. It has some thickness to it, but we're going to assume it's copper pipe. It's a drawn steel pipe, something like that. It's going to have a high K value, and it's going to be pretty thin really when you compare it to everything else. So we're going to make an assumption. It's a thin wall pipe. So this means that that pipe wall is thin enough that it doesn't count for anything. So your thickness is equal to 0, and the conductivity of your material goes to infinity. So essentially there is nothing we need to concern ourselves about the actual pipe in the analysis. We just drop that out. It's close enough to not being important that it's just not going to be important for our analysis. All right. Now we have done our design criteria. Remember, that is a lot of work, and it's going to be a lot of stuff that you're not even necessarily going to learn in school. You have company preferences, you have your preference. There's a lot more design criteria for the application, but this is what we chose. Now we need the plan. So the plan. There we go, put the plan. Boogie, 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 boogie. So we want to find how long this heat exchanger is going to be. That's what we're concerned about right now. We need to know how long to make the pipes in this heat exchanger. So we want L. To get L, we want AS, the surface area of the heat exchanger on the pipes. So we have a nifty equation we can pull out of our book here that can get us our AS. So here's our equation. Our net transfer units are equal to our overall convection coefficient multiplied by our surface area over our C minimum. So I need all this pretty much. I need that. I need that. I need that too. I'm kind of needy today, I know. Oh, I'm sorry, I need this. I need your overall convection coefficient so I can really get that AS. All right, let's get where all this comes from and get a plan going on here. So our overall convection coefficient is U equals HI minus 1 plus H0 minus 1 negative 1 over 1. So all this is it's like parallel circuits. That's all you're doing. You're putting it together and you get your overall convection coefficient. How about NTUs? Let's take a look at NTUs. We know that our NTUs, it's a lot like fin efficiency. We're using large, not very pretty equations to relate things together. That way we can solve for complex geometries. So our NTUs are a function of the efficiency of that heat exchanger and your CR value, which is your Cmin over your Cmax. So we need C. We need to find a C out of this. And to get the efficiency, we have a nifty little equation as Q, oopsie, as Q over Qmax is equal to our efficiency. So this is the heat transfer rate, this is the maximum heat transfer rate achievable, and this is our efficiency right here. And we also want the Cmin, which means we need C. So we really need our C, we know we need our U, we need our NTUs, and then we have to get an efficiency to make everything work. That's our plan. Well, I'm sorry, I hope you got to see the overall net heat transfer down here. Sorry if I got in the way. But that's what we need to do. This is our game plan. This is what we're going to do now for about the next hour together. And yes, it does take a while to do this. It is unfortunate, but these things do take time. All right, let's move on down. Let's find us a U. Write down your master equation. This is going to help you remember things. So let's start with the outside. So this is the convection of the air flowing through around these pipes and all these complex shapes. So you got this air and you're flowing around the pipe like 10,000 of them, and it's kind of hard. And we're gonna go with call a buddy. That's the solution here. We're gonna call a buddy, a specialist essentially. We're calling a specialist, and this specialist is going to do all our flow dynamics on a computer, and he's going to give us, because he's so awesome, he's going to give us our heat transfer coefficient going out at 300 watts per meter squared Kelvin. It took a little longer than it said to do. It really did. It takes a while to model these things, but he's so awesome. He saw what we're designing. He made a computer model, ran a simulation, and that's what he got for our values and temperature and all that. Done. We need this too. So, what's the first thing we do when we need to get a convection coefficient? We get us a Reynolds number, of course. It's always your first step, and that's always the right step. Now, this is for the water. Do we have the speed of the water? which is our U and our Reynolds number? No. But what else do we have? We have a mass flow rate. Well, near the beginning of chapter 8, you have an equation for the Reynolds number. I would make sure to remember that you have one of those equations. And it writes everything in terms of m dot. So it's the mass flow rate. It's just doing algebra for you, but it's really nice. Now, is there anything we need to change for this problem on this Reynolds number? There is. The D is related to cross-section. The diameter is related to cross-section in this equation. What's that mean for us? Well, it means that we don't have one diameter. We got 1,000 diameters. So multiply everything by 1,000 in this equation and everything's going to work out fine. So remember that. When you're doing these problems, if you do this Reynolds number for one pipe, you're going to get a really crazy high Reynolds number, and then it's going to whack everything else out because you're assuming it's only for one pipe. So make sure you have to modify that Reynolds number to include that. Don't make that mistake. Make sure to write your units. If you have the time to, go ahead and write those units. You do not want to make the mistake of not writing your units. And it is a mistake, especially on your exams. Okay, so we got a Reynolds number of 2,300, just a little over. Is this turbine or laminar? Well, we define our cutoff point at 2,300. But this is a real machine, and we do know that laminar can go above 2,300. Well, since it's a big machine and it's a real machine, you have pistons and it's shaking things back and forth a little bit. There's vibrations, boom, 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 boom. You also have a fan that's going whoosh. So you got boom, shh. And what that does is it creates some vibrations in the machine. Now what this means to us is that it's going to shake that fluid up. We can get laminar to go up above 2,300, but only under really nice conditions where everything's stable, nothing's changing. So we're definitely in the turbulent region. We say we're in turbulent because it's over 2,300, but we know we're in turbulent because it's a real machine, it's not stable. And then you have a whole pipe network coming to it that probably enhanced the actual turbulence of it to begin with. So it's turbulent. And is the flow fully developed? Well, we know that a fully developed flow for a turbulent condition is L over D is greater than 10. Oops. There we go. Greater than 10. So what does that mean to us? That gives us a definition for our intra-region as about L over D equals 10. So 10 L over D's is one intra-region on the turbulent. And our hydrodynamic and our thermodynamic intra-regions are roughly the same for turbulent. We assume they're the same for analysis. So we have a pipe that big, and we need a length 10 times that to have an intra-region. That would be our intra-region. That is our intra-region. Look how small that is. It's really, really tiny. Does this little intra-region matter? Well, we remember how big that current heat exchanger is on there. It's pretty big. I'm going to go with it probably doesn't matter. So we assume fully developed. So now we are not going to mess with the intra-region equations, and we're going to make our lives easier. And now let's go ahead and get us that H internal convection coefficient. And I want to grab something. I want to make my life easy. So we want to calculate that Nusselt number. Remember, you got to calculate your Nusselt number to get your HI. And it's going to be nice. It's going to be quick. It's It's going to be nice and beautiful, and we're going to be done here in just a moment. And there were some conditions on this equation. If I remember right, there was a condition. That's the condition. What's this saying? Our Reynolds number needs to be greater than about 10,000 to use this nice what was it? Boiter? Yeah, Dittus/Boiter equation. So is our Reynolds number even close to 10,000? Well, I don't think it's close to 10,000 at all. So that nice easy equation that we like to use, it's nice to use, it works great, but make sure you check your boundaries on when the equation is valid or not. These are all curve fits. They have nothing to do with physics. They're just fitting a curve. So they have an area in which they fit the curve well, and after outside of that area, it really falls apart and they deviate from the curve. So we can't use this equation. And we can't use the next equation in your book. We have to use that last equation, and if you're looking at it, you don't want to do it either. It includes the friction factor of the pipe. So let's go ahead and run through and get us that Nusselt number. And we do know, as unfortunate as it is, it's going to be a little bit more on the work side. But this is also going to help you for your exams. There's never too much practice. And we want to do it right because we got a lot of people and they need food. The last thing we want to be responsible for is explaining to our boss why it is that his multi-thousand-dollar motor here burned to the ground or has repair troubles because we didn't want to just go ahead and write a slightly longer equation. That would look really bad. I mean, it'd look really lazy. Let's check those boundary conditions one more time. And this is not looking good. This is not looking good right here. It's not quite within. And we're going to have to address this. Is our parental number good? Let's at least get that parental number out of the way. Well, yeah, our parental number's great. Our parental number is totally within the boundaries. It's like 1.6, 1.8. It's definitely within that boundaries. Now, what about the Reynolds number? It's 3,000 close to 2,300. It's close. What's these squiggly lines mean? Approximately. It's approximately 3,000. Do we have any better option? No better option. Unless you want to go online and try to find a better relation. But right now we don't have a better option and it should work pretty close. We're going to go ahead and use this equation. Now, if we use this equation, we have to find that friction factor. I know, we have one more side quest. Now we got to go find us a friction factor. So let's go and round us up a friction factor. Now, to get us a friction factor, we need to know what kind of roughness is on the pipe. Remember, friction factors, to find this, you need the roughness over the diameter. So we have a drawn tube. That's what we're going to be working with. It's a nice tube. It was produced by drawing it. And we're going to assume that that roughness from that tube is around 1.5 e to the negative 6 meters. So this gives you the average roughness of the pipe. Just like concrete, it has roughness to it. The average roughness would be the friction coefficient, and here it's pretty small with a drawn tube. So let's get that ratio, and this is what's important. It's not just about the friction, the roughness of the pipe. It's about the roughness of the pipe compared to the size of the pipe. So it's really just a ratio. And when we run these numbers through, that is going to be our roughness. So what do we need to do now? We need to go get us a friction factor. Where do we look? We always look to Moody's diagram. Where is Moody diagram in our beautiful book? Well, chapter 8, of course. Right near the beginning, that's where our Moody diagram is going to be. And looky there. There's our Moody diagram. There's our friction factor right here, this really hard to solve equation. Friction factor for a turbulent flow is not solvable linearly. So we either have to use a chart or we have to use a system of equations to solve it. Now, there are a couple different ways to do this. So what we're going to do is we're going to use our roughness over diameter, and we're going to use our Reynolds number to just follow the curve instead of calculating it out. There are a lot of different approximations, but we're just going to stick to the Moody diagram, which gives us real life data plotted, which is the best kind we can get. So our roughness to diameter ratio is 0.00015, so it's somewhere between here on the right side, right in between these two lines. So we follow the lines up, and we want a Reynolds number of 2300. So it's going to be to the 4th power. Should be right around here. We bring it on up. And where was this again? Well, it was right here. It converges on that smooth pipeline down at these low Reynolds numbers. Remember that. It's about the same. It's really not a big enough difference. We go up, and we're not sure where we land exactly, but we land over here. We know we land over here. Well, 0.05. That's pretty close. We have to interpolate a little bit, but our F is 0.05. Bam. That is our friction factor. Now we plug these numbers into our not so little equation. I know it's quite a big equation, but you get a lot of practice. Better now than on your exam. So we're just plugging in values. That's all we're going to do right now. All right, we plugged us in the values, and how are we going to solve it? Are we going to do it all at once for this equation? We're not going to do it all at once for this equation. When you get these big, not so pretty equations, go ahead and solve them in pieces. So we get the top. And then we get the bottom separately, and we calculate our Nusselt number. Now, what is our Nusselt number? Our Nusselt number, and the easiest way to understand it, is how well that fluid mix is. So how well does that fluid mix when it's going down this pipe under these conditions? That's our Nusselt number. Bam. It's an important number. We just highlighted it. Do we want a Nusselt number? No, we want our internal convection coefficient. Now, our internal convection coefficient is always equal to the Nusselt number times K. If it is for a pipe, it's over D. If it's for a flat plate, it's over L. So we run our numbers through. and we get around 670.2 watts per meter squared Kelvin. That is our H value. Did we want H? Let's look back up. No, we want U. That's what we want. We're going to want U, which we remember U. We have written this equation down a couple times. Hopefully you're getting it sunken into your memory. We plug in our values once again, and now we finally get what we want, which I know it's a lot of work, and that's just the way these problems are. As we go up in heat transfer, it's not necessarily that they're getting more complex, it's that they're getting longer to get these values, and there's a lot of bookkeeping and little details involved to get the answer. So that is our U value. So remember, our U is the overall convection coefficient for this heat exchanger. Bam, we got our U. Let's go back up. Let's see what we're doing next. So we go back up to the plan. What did we get? Bam, we got U. What should we do next? Well, we can't get into U's without our C's. We better go get some C's. So we find the C's. All right, let's do this thing. So when we're finding these C's, we want to do some bookkeeping. So we know that our air C is going to be an unmixed flow. Now we are making an assumption here that we're not mixing fluids across the pipes. Maybe we have some fins on these tubes. So when you have your tube array, you have your pipes in them, and we're assuming that air does not mix from over here and all around. So maybe there is some boundaries that keeps the air in, but we're going to assume it's unmixed. It's easier assumption. It will come into play later. And it's also known for the air as the cold. And then we need to know if it's the Cmin or the Cmax. Well, we're not sure yet. So let's calculate this out as equal to m dot Cp. We do not have the m dot for the fan, but we have the volumetric flow rate and we have the density. Now, when you calculate this out, we're not going to take the density at the median temperature. Remember, volumetric mass flow rate is a conserved quantity. Volumetric flow rate is a function of how much actual material is flowing times the density. So it's a little bit more than just one thing or the other. So that needs to be at the value that we're taking this volumetric flow rate. So we need to go back to table A-4, and we're going to have to assume that our T value is at the T inlet, and we're going to assume it's around 300 Kelvin. Remember, it was 321, but it's easier to do it at 300. So that should be a good approximation. Now all we have to do is plug the numbers in. Remember, this density is at the temperature of the inlet or the temperature where we got that volumetric flow rate from. Now our C value, what is it? It's the measure of how much energy it takes per second. So our watts, our energy per second, our power, to change the fluid by 1 degree centigrade. In this case, it's centigrade, or by 1 degree of your temperature units. So in this case, it takes 34,000 watts to change the fluid temperature by 1 degree. That's how much power it takes to change that fluid temperature. And we're going to roll on out, we're going to do the same old thing for water. So we know water is unmixed. Why is it unmixed? Because we have 1,000 pipes. Fluid is not mixing between those pipes. Once it goes in those pipes, it goes out. And it goes back and gathers later, but it's not mixing when it's in that pipe, in that heat exchanger. So it's an unmixed. We know that this is hot, and we need to know if this is the max or the min. We'll come back to that. Same process, m dot Cp. So it is 5 kilograms per second. And remember, this Cp here is a lot larger than that Cp for air. So it takes a little more energy to change the temperature of water than to change the temperature of the air. So when we calculate it out, we get 21,100. Now we get to figure out who the winner is, who's going to absorb more energy before changing in temperature. That's air. That also counts as Cmax. Who's going to change a lot faster temperature before adding the same amount of energy? It's going to be that water. That's going to be the Cmin for this problem. There's one other C we're concerned about. That's the CR. We need it for the efficiency. CR is nothing more than Cmin over Cmax. So we have 33,700 for our Cmin. Oh, I'm sorry, that's Cmax. So our Cmin is 21,000, essentially. And it's really important that you remember to keep the ratio right. So our CR is always between 0 and 1. If your CR is ever greater than 1, you've made a mistake in assuming which one is your Cmin and your Cmax. Remember that if it is ever greater than 1, you've made a mistake and you have to go back and fix it now. All right, that's done. We've got our C's. Let's roll back up on top real quick. All right, we calculated our C's. Bam! We are on this table a third of the way done. Now we need to calculate our NTUs, but to get our NTUs we need an efficiency. So we are getting and drawing nigh to the end of this problem. I know it's felt like a long time. It has been a bit of a long time, but we are slowly approaching that end. These problems are long, and it takes longer to solve it the first time. It really does. So we want to find the NTUs, and first we have to find the efficiency. So let's start with that efficiency. What's our efficiency equal to? It's equal to the energy coming in time over the maximum energy potential. So what do we have here? What do we know for Q? Well, do we know it's going to be a C, which is our m dot, our mass flow rate, times our Cp value, which we know from earlier in our walk with heat transfer, times the delta temperature. So the air coming in, do we know the temperature of the air coming in for certain? Sorta. Yes, we know our maximum temperature that it can be. Great. Do we know the temperature that it has to go out as? Maybe. We stuck a measure down there and took a look, but really it doesn't have to leave that temperature. How about the water? Well, we know the maximum safe temperature for that water, and we know for certain when we run it through the heat exchanger, how cool it has to be when it gets back to the motor. So we know that. Let's solve our Q for water because that's more certain when we do this equation. So our C is for water. It's also known as our C min. We have our hot coming in and our hot going out. Bam, problem solved. Now we want our Q max. This is just like fins. So we want our C min because you can't have more Q flow than out of the minimum one. It controls the rate that heat can flow. So the fluid that's going to be changing the most with your temperature is going to be the limiting factor because it's going to rise in temperature first and it's going to prevent further heat transfer. Now it is our maximum temperature difference. Remember way back up top when I told you that was important to know the delta max, the maximum temperature difference? It's our hot inlet minus our cold inlet. That's why it was important. So let's roll back on down. Our hot inlet minus our cold inlet. Bam. And look at how nice this is. Bam, bam. We have just gotten rid of some part of our equation. And it's always nice when we can cancel things. So we want to calculate that efficiency out now. All right, and that's going to be about 0.6. Now we want to find our NTUs. Now what do we know about our NTUs? Well, we know that our NTUs are a function of our CR and our efficiency. That's why we just calculated efficiency. We got the CR, we got the efficiency, we are ready for those NTUs. All right, now what is an NTU? It's just another form of relating heat transfer. So it is net transfer units. It's just a way to non-dimensionally relate different factors in a heat exchanger that we can't really solve for when we're doing derivations. It's not really solvable when we have a really complex geometry to do a derivation for. We want to do something experimental and have a way to relate it. It's similar to your shape factor. All we're really doing here is we're having a shape factor for our heat exchanger. Heat exchangers have complicated geometry. Sometimes they have fins on them. Sometimes they have little things inside them to give them secondary flows to transfer heat better. But essentially, all these NTUs and efficiencies do is they give us another way to solve the problem from experimentation using a shape factor. That's really what they represent. They're just taking a complex problem, they're making one condition and giving you an approximation for this type of heat exchanger, what the numbers are going to come out like. They're just there to make your life easy. So, what do we know about a heat exchanger? It is a shell and tube heat exchanger. And it is a one shell. It is a one shell pass. We only have one shell in the heat exchanger and it's a shell and tube type. So what are we going to go do? We're going to go to table 1, 11.4. So table 11.3 is converting NTUs to efficiency. Table 11.4 is taking efficiency into NTUs. Let's take a look here. We know that's chapter 11. And we work our way on down. We work our way into table 11.4. Now let's take a look at 11.4. Bam, shell and tube heat exchanger. Bam, we have a one shell pass heat exchanger. We get some equations. There are no special conditions. So here we are. Everything's working out really nicely. We go back, we record these equations down. So we get our NTUs is equal to some complex function relating a lot of C's and efficiencies together. Now, if you look here, when they did this, they put this variable E in. E is not something we have to go do more work to calculate. E is just taking this function for NTU and putting it, part of that function, into something simpler. It's just making bite-sized chunks. Like I said earlier, we like as engineers to simplify things and make bite-sized chunks. Whenever we're doing complex problems like this, it saves a lot on calculator error. Bam, so we want to solve. We want to plug those numbers in. And this is really just a numbers game at this point. We're not doing anything that requires too much thinking. We're just plugging and chugging numbers. I wish I could say it was a little more. Now, if you look here, our efficiency and our CR values are very similar. This was not by design. This was a completely random occurrence. So if you're wondering why that happened, it just went ahead and happened. I'm not even sure why. Now we get our E. Now here's somewhat of the problem of using some of these shape factor problems and breaking stuff down. I don't know if E's a good number. I don't know if it's close. I don't know if it's crazy to say that E is this. I just know we calculated E and this is E. So that is one of the problems with using some of these non-dimensional things like NTUs. We really aren't sure if we got a good value for it, if we calculated it right. We don't have a feel for it. If we calculated the speed of a car when we increase the horsepower by like 20 and it goes 300 miles an hour, we know that somewhere on our end we messed up. But with some of these NTUs and these complex functions, we're really not 100% sure because we don't have that way to feel them. So we get this net transfer unit number of 1.7237. Good number, bad number, I don't know. Bam, we're done. Now we go back to our plan. There we go, the plan. So what's our plan now? Well, we went through, we got our efficiency, we got our NTUs. We are ready to actually solve the problem now. This entire time we have been solving all these numbers that we need to solve the problem. And it's kind of humorous because this problem is going to be easy to solve now. It is easy as can be from here. So we want to find the length that we're going to need for this heat exchanger to work, and then we got to find the surface area. So remember this equation we have that relates everything together? Now we want to solve for AS. What is AS equal to? Well, we look up here. AS is going to be equal to NTUs times our Cmin over our overall convection coefficient U. What else is the surface area for the pipes also equal to? Well, it's equal to the surface area of a pipe, which is going to be pi d. Now that pi d, part of this equation here, this gets you that circle in one dimension, that circle around the pipe. And then we want to integrate that with respect to length, which is with respect to L. And we want to multiply that all by the number of pipes in this system, which is 1,000. So I just want you to understand where some of these numbers come from, because I know sometimes on a paper they look like they're just there, but they really all have good meaning. And as an engineer, you need to know a little bit more about the meaning, because that's what you're being paid for. It's easy to hire someone to work a computer, but it's hard to hire somebody that actually understands what the computer is doing and understands how to work it in that way, the actual meaning of things. And now we just plug in those numbers. All those numbers we calculated way back, we just plug them on in here. I am cheating a little bit. I probably should put the units down, but they should all cancel. That's also why I said make sure everything is in your base unit system, because all these units will cancel out so that we get L is equal to 5.5837 meters, which I probably don't need to calculate it out to that many decimal places, but we did. Now, it's important to remember, actually let's do one more thing first. So we have our pipe going through our heat exchanger. It looks like that. RL is going like this. That's L. We're going to want L over 2. It tells us how long this heat exchanger is going to be. It's nice that we have L, so L over 2 is roughly equal to 2.8 meters. That's roughly how long this heat exchanger is going to be. So after all that work, that's what we get. We get to know, after this design choice, roughly how long this pipe is going to be in this heat exchanger. So let's go back and take a quick recap, just so we make sure that we remember what we learned. We got a heat exchanger. We are working in Alaska. We're modifying a motor, essentially, a generator assembly. And we got all these values here for our heat exchanger. We looked stuff up, we went and measured stuff, and this is what we got back. This is the closest we can get it. We went through and found our values in the tables. We learned to love our heat exchanger book. We learned to love it so much the front cover comes off. That's how much we love our heat transfer book. So we got all our values from our medium temperatures, not our inlet temperatures, not our outlet temperatures, our mean temperatures. We designed a heat exchanger. A lot of company policy, a lot of personal choice, a lot of other design considerations, including how that manufactures, what way is going to be best in that sense. We define an overarching plan, a general equation that we want to get all the pieces for, and then we went and found the pieces. We needed our overall heat transfer unit, convection coefficient, and we needed the internal convection coefficient and the external convection coefficient. External convection coefficient we called the buddy. The buddy modeled it for us. He gave us the value. We found the internal, went through the Reynolds number, found the Wright-Nusselt number equation. Remember, the Wright-Nusselt number equation is the one where all the conditions for the equation match up. In this case, it matched up pretty close and it was the best option at hand. But remember, this is the difference between you being a successful engineer and you being somebody that knows how to work a computer. You understood why we got the equations and where we got them from and what's useful and applicable to our situation. We run on through. We had to get a friction factor for this equation, for this Nusselt number, to calculate it out. We had to get our roughness for a drawn tube approximately, and then we just run through our numbers, run through our U, everything goes right back together. We're done. We had to find our C's next. So we wrote down all this information about our C's in case we need it. I recommend you do this with every problem. You don't want to make that mistake in the middle of an exam that you mixed up which is your cold, which is your hot, your max, your min. Write it all out, calculate the numbers out. You're good to go. CR, that was just the ratio between the C min and the C max. It's always between 0 to 1. And remember, for that error that we calculated, we had to get the density to multiply by the mass flow rate at the temperature at the inlet where we measured, where we have the known value of that volumetric flow rate. So remember, get the value for density at the point you have the speed or the volumetric flow rate. And to use, it's another form of Finn equation. It's like a shape factor. It's essentially modeling more complex systems, just having an approximation, a factor. Somebody else set up some experiments or derived something for us to make our life easy. So to calculate NTUs, we need the efficiency. Since we knew the maximum safe limit of the water coming in and going out, we were able to use that to find Q. Q max is equal to the maximum heat transfer that can happen. Found the efficiency. We learned that NTUs are a function of CR and efficiency. We looked up in table 11.4. We ran our numbers through. We got our NTUs. End of the problem. We wanted to find our length. We wanted to know how long this thing is going to be compared to the original. And to do that, we had to find our surface area. We got our equation here in terms of its surface area. And then we got the surface area as a function of the actual pipe sizing. Then we just solve for length, plug numbers in, got our length, got our L over 2, which shows us how long this heat exchanger is going to be. And this is our first iteration. We would want to do some more iterations. We also want to keep in mind some things when we find this out. Our convection coefficients, they can be off by 10%, they could be off by 25%. So it's not certain. Some of our NTU approximations, depending on how that inside of the heat transfer unit is built, it may not be exactly how we calculated it. It may be a little off. There's going to be some error. So whenever we run through these problems, we're really proud of our engineering and our skills, but it's really important to remember that there's a lot of approximations that we put into this problem to get it to a point that we can get a numerical answer to put stuff together. So just keep that in mind. I hope you learned a lot. I hope this is going to help you study for your final. And I really thank you for taking time to finish this video. You have a good night.